Have you ever noticed a problem? Why does the universe have rules and constraints? Logically speaking, randomness and chaos should be the more natural state. Yet we live in a world that everywhere follows order, from the motion of electrons to the rotation of galaxies, from the speed limit of light to the minimum Planck length. They all seem to obey an invisible cosmic code. The question is, who set these rules? Were they just inherently there, or were they deliberately designed? But merely knowing what the rules are is not enough. The real challenge is understanding why they work. So next, we will follow this question. Step by step, peel back the shell of the universe to see whether order is in control of everything, or if chaos is the true master behind the scenes. And to find the answer, we must first start from the most fundamental and also the most mysterious starting point. That is the principle of invariance. You can drop a ball in New York or conduct the same experiment on the moon. The result will be the same. It will bounce in the same way, because the fundamental laws of physics do not depend on location. Thus they remain consistent no matter where you are. In any corner of the universe, from the tip of your pen to the center of distant galaxies, it is all the same. And this characteristic of rules, not changing with location or time, is called the principle of invariance. This means reality is not a chaotic collection of strange phenomena randomly pieced together, but a complex and consistent whole structure. The reason it can maintain this consistency is because there is no so-called preferred position or special moment in the universe. No matter where you move the experiment, or change its orientation, or even run it at different times, the results will be exactly the same. And whether you measure the charge of an electron, the energy of a photon, or the gravitational effect of a falling apple, the underlying equations are always the same set. And precisely because of this symmetry is the foundation of the universe's uniformity. More crucially, the power of the principle of invariance is not just because the mathematical forms look consistent, but because it ensures that physical laws must hold everywhere. Otherwise, the universe would become a random monster. Galaxies might be forming in one place while collapsing in another, and the patterns we used to determine our place in the universe would be completely disrupted. In fact, we verify the principle of invariance every day. For example, by moving an experimental setup to a different location for testing. In particle accelerators, we collide protons at extremely high energies, and no matter where the accelerator is built, the observed interaction behaviors are the same. If one day a detector in Europe suddenly fails to detect a certain particle, while a detector in Japan can, that would indicate a fundamental problem, but that is not the case. Every experimental station, every telescope, every instrument yields consistent results. This shows that we live in a universe that follows unified rules, and Einstein's theory of relativity is almost entirely built upon invariance. He insisted that the laws of physics, including the always constant speed of light, must appear the same to any observer, no matter how they are moving. It is precisely this principle that sparked a scientific revolution. The concept of simultaneity was overturned. Space and time merged into a dynamic whole, gravity was redefined as a manifestation of geometry, and all of this is because physics remains unchanged under motion. At the same time, invariance is directly related to the conservation laws we rely on and trust. For example, energy must be conserved because physical laws do not change with time. Similarly, momentum remains constant in space because physical laws do not depend on an object's position. Next, Emmy Noether would precisely explain this connection with mathematics. Similarly, the principle of invariance also explains why science is universal. Astronomers, chemists, engineers can build telescopes to probe the depths of the early universe, and the patterns they discover and the phenomena they measure all follow the same physical laws that make your phone's battery work. Therefore, without invariance, we would have no reason to trust the observations sent back by the James Webb Space Telescope or Mars rovers. Thus, invariance means our physical models are not just snapshots of some local region, but truly global truths. However, how far does this invariance extend? Does it hold everywhere and at all times? This we are not certain of. Perhaps in the early moments of the Big Bang, or under the extreme conditions of quantum gravity, it might break down. But until such cracks are discovered, it remains the strongest glue holding reality together. Maybe one day we will find that nature's ultimate invariance is not absolute, but only approximately true or even breakable. Until then, every precise test supports its existence. This is not luck, but more like a signal. The way nature is constructed seems to allow itself to be understood and transmitted consistently. This leads to an important conclusion. If physics is constant, then the concept of vocation loses meaning. This means even if you and an alien from billions of light years away are separated by countless spans of space and time, you can both use the same methods to measure gravity, electrons and photons, and the results they obtain in their laboratory will be exactly the same as yours on Earth. Even if the names of their tools are completely different, their DNA and societies might be entirely distinct, but their atoms still obey the same rules as yours. It is this cosmic consistency that gives science itself meaning. In other words, we are not collecting a pile of peculiar phenomena from various places, but searching for a universal language. The universe is not composed of isolated islands, each with different physical rules, but a whole governed by unified laws. So why does physics always work? Because the foundation of the world is built on invariance. This means no experiment, direction, or era can change nature's way of operation, and that is why we believe stars shine in the same way in any space and time. Electrons have the same charge no matter where they are, and the conclusions you draw from studying the tiniest particles on Earth also apply to the edge of the observable universe. Moreover, the symmetries in nature are the blueprints hidden behind the laws. Imagine rotating a snowflake. Whether you turn it 60 degrees or not, it looks exactly the same. This is symmetry, meaning an object remains in the same state after a certain transformation. However, in physics, symmetry is not merely about making shapes look beautiful. It is the key that links all the forces, equations, and particle interactions we have measured. In fact, Symmetry is so important that it is sometimes called the language of natural laws, or the secret code that makes everything from electrons to galaxies make sense. In physics, symmetry refers to a system remaining unchanged under a certain transformation. This transformation could be moving a particle's position, rotating it, mirroring it, flipping it, or even swapping matter particles with antimatter particles. If the equations describing this system are completely unaffected after such a change and still hold, then it possesses this symmetry. And what is so remarkable about this, because each symmetry corresponds to a conserved quantity. No matter how the system evolves, this quantity remains unchanged. For example, if physical laws do not change with time, energy is conserved. If they are unchanged, then space momentum is conserved. If they are unchanged under rotation, angular momentum is conserved. This deep connection between symmetry and conservation laws is not just a coincidence, but a strict mathematical truth. We will delve deeper into this with Noether in the next part. Similarly, the generation of forces also originates from symmetry. Think about it. Electricity works because our handling of electric charge follows a specific symmetry. Likewise, the existence of the strong and weak nuclear forces stems from more abstract internal imbalances. These symmetries cannot be visualized with simple rotations or mirrors because they exist in mathematically described spaces where quantum properties like charge, flavor, color can all change as long as the equations still hold. The symmetry remains, but once the balance is broken, things become interesting. In fact, most of the structure of our world originates from broken symmetries. In the early universe, all the forces might have once merged into a perfectly unified whole, but as the universe cooled, this unity gradually broke apart, giving birth to the separate fundamental forces we know today, like taking a perfect snowflake and slowly heating it. Its petals gradually melt, leaving a new form that is no longer symmetric but still stable. And particles like electrons and quarks, bosons, their masses come from such spontaneous symmetry breaking initially. The Higgs field that gives them mass was balanced, but this balance was later broken. Once this symmetry is broken, particles begin to interact with the Higgs field, and thus mass emerges. Symmetry does not exist only in particle physics or the early universe. It is everywhere. In chemistry, the shapes of molecules often follow the rules of symmetry. In biology, from butterfly wings to zebra stripes and animal patterns are determined by symmetric developmental processes. Even in economics, some models rely on symmetries about behavior and probability. It seems nature always starts with symmetry and only actively deviates from this balance when it needs to gain something, like structure, mass, or diversity. In mathematics, symmetry is closely related to group theory. Group theory is a branch of algebra that studies transformation rules. Every known fundamental force in physics can be described by a symmetry group. For example, the standard model of particle physics is entirely built on these principles, using mathematical groups such as SU3, SU2, and U1. Don't worry about the details of these symbols. Just know these groups describe how particles behave, how they interact, and the changes they can undergo without breaking physical rules. And the more we understand about the universe, the more we discover that symmetry might not just be a useful tool, it might even be the hidden scaffold upon which reality is built. If you were to design a stable, predictable, yet emergent universe from scratch, then the most reasonable approach would likely be to first establish a set of symmetry rules. However, not all symmetries exist. Why must electric charge be conserved, while parity is not conserved in weak interactions? Why do particles obey certain mirror flips, but ignore others? Nature seems to selectively use symmetry, sometimes even deliberately breaking it, as if following an unknown script, finding balance between elegance and complexity. And this raises a bigger question in science. Do the physical laws themselves originate from a deeper, more perfect symmetry? Perhaps the universe we see today, with all its flaws and asymmetries, is just the shattered remnant of a more perfectly symmetric reality, like a once complete statue, cracked over long ages, weathered and eroded. And this is precisely the question Noether's theorem aims to answer. Where do the laws in mathematics ultimately come from? You might have heard the phrase, "For every action, there is an equal and opposite reaction." But what if I told you nature has a protective rule for every symmetry, and not just logically, but a strict mathematical fact? That is the entire meaning of Noether's theorem. It is one of the most important ideas in theoretical physics, coming from the German mathematician Emmy Noether. Her idea quietly changed the way we understand the entire world. In the early 20th century, Einstein had just proposed general relativity, redefining gravity as the geometry of space-time. However, problems soon arose when trying to apply traditional conservation laws, like energy conservation, to Einstein's new framework. The results became ambiguous and curved, dynamic spacetime. Physicists even struggled to define what energy really meant. It was then that Noether stepped in. In 1915, she proved something astonishing. Every symmetry in a physical system corresponds to a conserved quantity. This is not just a useful observation, but a rigorous mathematical law. For example, if physical laws do not change with time, that is, time translation symmetry, then energy must be conserved. If they do not change with spatial position, spatial translation symmetry, then momentum is conserved. If they are unchanged under rotation, rotational symmetry, then angular momentum is conserved. And this pattern holds the deeper you look. For example, how electric charge is conserved is directly related to the symmetry of electromagnetic field equations. Even conservation laws can arise from more complex symmetries, like gauged transformations or internal quantum numbers, as long as they are continuous and differentiable. The special thing about Noether's theorem is it doesn't just list the rules of physics. It explains the source and necessity of these rules. Before her, scientists knew some quantities remained unchanged, but no one could fundamentally explain why. After her, people understood that conservation laws are the consequence of symmetries. You don't even need to start by writing down conservation as a rule. Just assume nature doesn't care about certain transformations, and conservation laws automatically emerge. For analogy, if you were designing a physics engine for a video game, you wouldn't need to separately code a rule for energy conservation. Just ensure the engine doesn't calculate physics differently from 1 second to the next. Energy conservation would naturally hold. The same goes for space and velocity. Rules are automatically written by symmetry. This is not merely convenient, it is the foundation of physics. In quantum field theory, which underpins the Standard Model, Noether's theorem occupies a central position because every fundamental interaction has a symmetry group. Describing electromagnetism as U1 symmetry, weak interaction is SU2 symmetry, strong interaction is SU3 symmetry. These are not just mathematical tricks, they directly determine how particles and interactions themselves exist, and Noether's insight even influences modern cosmology. Like inflation theory, this theory suggests the early universe, once expanded faster than light, relies on the idea that vacuum symmetry can break, releasing energy and shaping space-time structure. It can be said Noether's imprint is found almost everywhere in modern physics. Since every symmetry corresponds to a conservation law, what happens when symmetry is broken? Then things become even more interesting. In physics, spontaneous symmetry breaking refers to a system's fundamental laws being symmetric, but its actual solutions no longer reflect this symmetry. Imagine a pencil balanced vertically on its tip. The law is completely symmetric, but once it falls, it chooses a specific direction, thus breaking the symmetry, and whenever symmetry is broken, new things are born. For example, the Higgs mechanism that gives particles mass comes from a symmetry breaking. The diversity of particle types, the formation of atoms, even the structure of the universe can be traced back to those moments when perfect symmetry moved toward complexity and diversity. As for Emmy Noether herself, she had to face considerable prejudice in her time, brilliant and talented. Yet for years she could not teach under her own name, even had to publish some important work anonymously. Despite this, her contributions are now considered one of the most important achievements in the history of physics, even praised by Einstein as a monument of mathematical thought. Speaking of another cornerstone of modern physics, that is gauge fields. They are the invisible structures governing various forces. On the surface, our world is made of planets, particles, atoms, and stars, but if you peel back the layers carefully, you'll find a completely different scene. Fields that exist in space yet cannot be seen directly. These fields control all the forces you experience. Gravity pulls you to the ground. Magnetism makes compass needles spin. Electricity breathes life into machines. And behind them are gauge fields. They are not just background, but the hidden scaffolding of reality, a mathematical structure dictating how particles move, how forces arise, and why the universe can maintain order. A gauge field is a field defined by symmetry. This symmetry is not of shape, but of the rules themselves. For analogy, it's like designing a game where players can freely choose any color for their outfits, but the game's outcome doesn't change because of it. This freedom to choose colors without affecting results is a kind of gauge symmetry in physics. This means you can freely change the state of a field at every point in space. while the final physical result remains unchanged. To preserve this freedom, natural laws must introduce a corresponding gauge field. Electromagnetism is the most famous example in quantum electrodynamics. The electromagnetic force originates from a U1 gauge symmetry. This is a way that allows quantum fields to rotate freely. When you make this symmetry local, meaning each point in space can independently rotate its field, you find that a photon must appear. Yes, the electromagnetic field that produces light, Wi-Fi, and lightning does not inherently exist. Its emergence is a result of mathematical balance. This rule holds for all fundamental interactions in the Standard Model. Weak interaction originates from SU to gauge symmetry. Strong interaction comes from SU3. These are not just abstract terms. Each describes how a field can change and how particles respond. Those force-carrying particles, like W and Z bosons, gluons, photons, are essentially the messengers of symmetry. In other words, forces do not exist out of thin air, but are enforced through fields by symmetry. So what is truly important here? The power of gauge theories lies in they not only describe forces, but can predict them. Once you choose a symmetry group, the types of particles and their interactions naturally emerge from the mathematics. Mathematics itself writes the universe. For example, if you want to describe the strong interaction that binds quarks inside a proton, just write an SU3 gauge field into the Lagrangian. You'll get 8 types of gluons and a complex dance of color charges. These equations do not live in empty space, they shape space itself. In some quantum gravity theories, space-time might even emerge from gauge interactions. In string theory, gauge fields are fundamental elements. Tiny strings vibrate not only in position, but also in gauge space. In loop quantum gravity theory, the loops that weave space-time are precisely outlined by gauge connections. That is to say, the geometry of reality and the structure of forces might not be separate, but the same thing viewed from different angles. Gauge symmetry tells us physical laws do not care about arbitrary choices. You can change reference frames, rotate a field, tweak a parameter. The mathematics still holds. But to keep the mathematics consistent, nature demands some form of compensation, and this compensation is the gauge field. Is like tuning a piano. You can choose a new reference pitch for each note, but to keep the music harmonious, you must adjust the intervals in physics. These intervals are force fields. Their existence is to maintain the harmony of symmetry. Sometimes gauge fields interact with each other. For example, the strong interaction consists of gluons carrying their own color charge. Therefore, quarks can never be separated individually. The more you try to pull them apart, the stronger the force becomes. In contrast, electromagnetic fields are not bound to each other, so you can separate positive and negative charges. The personalities of different forces are determined by their underlying gauge group frameworks. As for the Higgs field, it itself might be a gauge field. Its role sounds simple, that is, giving particles mass, but the result changes the entire landscape of particle physics. Without it, W and Z bosons would have no mass. Weak interaction would not be the weak force we know today. In fact, Every time you feel gravity, electromagnetism, or nuclear forces, you are interacting with gauge fields. Every rule in nature, from how particles spin to how they scatter, is governed by this invisible network woven by symmetry. But a bigger question is, why exactly do these specific gauge fields exist? Why SU3, SU2, and U1? Why do the equations precisely need these structures and not others? Physicists are still searching for answers. Some think the symmetry is actually larger, like SU5 or sulfur monoxide 10, but was broken into the forms we observe today. Others, starting from string theory, believe gauge groups emerge from the geometric structure of extra dimensions. Some even speculate gauge symmetry might just be an approximate manifestation of some deeper preset structure at low energies. Next is another fundamental concept: Planck units. Nature's built-in measuring system. The meters, seconds, tons we use daily are actually all human-defined based on random references, like the length of a silver rod in France or the time it takes for Earth to rotate once. They are useful for communication, but do not belong to the universe itself. So if we remove all human definitions and keep only the universe's original language, what remains? This is the meaning of Planck units. In 1899, Max Planck proposed a set of measurement systems completely independent of human conventions, based solely on nature's fundamental constants, like the speed of light c, Planck's constant h, and the gravitational constant g. These constants are the universe's native code. When we measure in Planck units, we are not asking how many meters it is, but how large. It is compared to the smallest structure reality allows. For example, the Planck length is about 1.6 times 10, 35 meters. Extremely tiny, a proton is 100 million times larger. It is not just a very short length, but the scale at which space begins to lose its continuous meaning on scales smaller than it. Quantum effects might become so strong that space-time tears, blurs, or even completely disintegrates. Many theories suggest the Planck length is the boundary where smooth space-time structure collapses into quantum foam correspondingly. Planck time is about 5.44 times 10⁻40 for seconds. This is the smallest meaningful time scale in physics. Shorter than this, it becomes impossible to define sequence. Time might become discrete, jittery, or even cease to exist. Planck mass, on the other hand, is quite large for particle physics, about 20 micrograms. This mass scale is especially important in quantum gravity because it is roughly the threshold where quantum gravity effects cannot be ignored, and the mass limit at which a particle might collapse into a miniature black hole. These constants are not just technical details, but the fundamental parameters that determine the stage for all events in the universe. When you combine them, Planck's constant h, the speed of light c, the gravitational constant g, what you get is not strange mathematical results, but a natural operating system. Unlike meters or pounds, Planck units have the same meaning everywhere. If an alien civilization at the other end of the universe built physics from scratch, they wouldn't use inches or feet, but would certainly know the Planck length, because it does not depend on their planet's size. language, or biological structure, only on how the universe itself operates. Some physicists even view Planck units as the underlying code of reality, like a video game. Having a minimum pixel size and frame rate, the universe might also have a fundamental resolution, and the Planck scale is precisely its definition. Any phenomenon smaller or faster than it would not be supported by the system. However, there is an even deeper mystery here. Why are these constant values exactly as they are? Why is the speed of light about 300 million meters per second? Why is Planck's constant so incredibly small? If even one of these values change slightly, the universe might become unrecognizable. Atoms could not exist stably. Stars could not form. Life would be impossible. Yet their values happened to be exactly as they are. The Planck unit system does not explain why these constants take these values. It only tells us how to combine them into an innate natural scale. From one perspective, Planck units are extremely elegant. They point to a universe indifferent to human wishes, a universe that can be described in terms of true and false. But on the other hand, they raise unsettling questions. Are these constants really that fundamental? Or are they just placeholders, rough guides to grander concepts that we are far from fully understanding? Some scientists believe the constants we know, like the speed of light c, Planck's constant h, and the gravitational constant g, might originate from something deeper. They might just be manifestations of some more fundamental structure at low energies. These values might change at higher energies or in other regions of the universe. If that is true, then no matter how powerful the Planck system is, it is only a regional accent in the broader mother tongue of physics. There is an even bolder idea that reality might not be physical, but digital. If so, Planck units represent the smallest information pixels, the indivisible minimum units of space, time, and mass. Then physics would be like a program running on a cosmic computer, and the Planck scale would be the ruler for this computer's grid spacing. This idea resonates with quantum gravity, loop quantum gravity theory, and even the simulation hypothesis. In other words, when we ask what the natural units of the universe are, we are actually asking, what are the underlying settings of this universal operating system? Planck units are like the default settings of physical laws, the universe's safe mode. Understanding them might be the key to rewriting the universe's underlying code. Yet even though they are so elegant, they are almost invisible. No experiment has ever directly probed the Planck scale because the required energy far exceeds current human capability. Only extreme environments like black holes and the Big Bang can truly touch these boundaries. Next, we must face another mystery. Why there is a speed limit, that is, the origin of the speed of light. A speed limit in the universe was set long ago and cannot be changed. In a vacuum, nothing can travel faster than light. Approximately 199,792,458 meters per second, or a little over 300 kilometers per second. No matter how powerful your rocket, no matter how much energy you pump into a particle, or how wild your ideas, this limit cannot be broken. And this speed limit does not belong only to light. It is the universal speed limit for everything. So why does this limit exist? To understand it, we must first change our traditional understanding of speed. According to Newtonian mechanics, speed is space divided by time. This concept is simple and intuitive, and theoretically can increase or decrease without limit. To go faster, just push harder, double the force to get double the speed. But Einstein's 1905 theory of special relativity shattered this myth. He showed that space and time are not two independent concepts, but two parts supporting the same fabric. This fabric is called space-time, and space-time itself has its own rules. When an object's speed approaches the speed of light, its motion approaches this limit more and more slowly. Mass increases accordingly the closer to light speed. The more energy is required to increase speed even a little. When your speed reaches 99.9999% of light speed, additional input energy almost no longer increases speed, but makes you heavier. The speed of light is like a wall in space-time that any particle with mass cannot cross. Why? Because the speed of light is not just a speed value, it is the proportionality constant defining the geometry of the universe. In the equations of special relativity, it links space and time together, like a conversion rate between meters and seconds. If space-time is the stage on which all physical phenomena play out, then the speed of light is part of the stage's skeleton. Light itself is not the cause of this limit. It just happens to travel at this limiting speed. Photons can reach the universe's maximum speed because they have no mass. No mass means no resistance. They can naturally travel at this maximum speed. If massless particles did not exist in the universe, we might not even know there is a speed limit. Light is just the most easily observable messenger. So the key point here is not that light itself is special, but that the geometry of space-time itself dictates that massless things move at this speed. This is not light's choice, but a property of the universe. This brings us to James Clerk Maxwell's electromagnetic theory from the 1860s. While organizing electromagnetic equations, Maxwell discovered a strange result. They predicted that electromagnetic waves always propagate at a fixed speed. When he plugged in the known constants of his time, this speed turned out to be exactly the speed of light. Light is essentially an electromagnetic wave, not some mysterious glow, but an oscillation of electric and magnetic fields intertwining in a vacuum, and the behavior of these fields is governed by two fundamental constants: vacuum permittivity and permeability. Combining them gives the speed of light c. In other words, c is not an independent speed, but the inevitable result of electromagnetic field propagation in a vacuum. If you change the laws of electromagnetism, you would change c, but then the entire space-time structure and all physical laws depending on it would collapse accordingly. New questions also arise. Why exactly this value? Why not 1,000 kilometers per second, nor 1 billion kilometers per second, but about 300,000 kilometers per second? No one truly knows. If we used a different measurement system, for example, not using meters and seconds, this number would become something else. And in natural unit systems, like Planck units, The numerical value of C is 1. This shows it is not an arbitrary number, but a proportionality scale built into the universe's underlying code. Some theories suggest C might be directly tied to causality. If information could travel faster than light, paradoxes could arise, like messages from the future, effects before causes, or even complete disorder in time sequence. Special relativity, by setting the speed of light as the limit, preserves the causal chain, keeping time stable. Some bolder speculations, the speed of light in the early universe might not have been today's value, or might even have been higher. Such variable speed of light theories have been used to explain a puzzling cosmology problem, namely, why the universe we see from extreme distances today is so neat and orderly. The usual explanation is inflation theory, but if light speed were higher in the early universe, it might also solve this puzzle. However, there is currently no conclusive experimental evidence. Others suspect the speed of light might not be the universe's ultimate limit. Perhaps gravitational waves or some unknown interaction can be faster, but so far, whether in particle physics, astronomy, or gravitational wave observations, all results consistently indicate C is the ceiling. For us, this means interstellar travel can never be as easy as in science fiction. No warp drives, no hyperspace jumps, unless we find loopholes like wormholes or quantum tunneling. Until then, the speed of light is an insurmountable limit. Next, we face another puzzle, that is, the parameters of the standard model. Who set these cosmic knobs? Imagine facing a dense control panel lined with many knobs, each precisely tuned to a specific position. These knobs control everything from how electrons move around nuclei to how quarks bind tightly inside protons. They determine the strengths of fundamental forces, particle masses, and how they mix and decay. Strangely, these knobs really exist, and they all belong to particle physics' standard model. The standard model is our most successful theoretical framework so far for describing the subatomic world. It covers 3 of the known fundamental forces, namely electromagnetism, the strong nuclear force, and the weak nuclear force. It includes all known elementary particles, including quarks, leptons, and bosons. For half a century, it has withstood countless experimental tests and remains standing. However, it has at least 19 free parameters, meaning these values must be manually input, not derived from a deeper theory. They seem independent, yet together maintain the universe's operation. For example, 6 different quark masses, from the very light-up quark to the top quark heavier than an entire gold atom, then the lepton masses, including the electron and its ghostly relatives, the tau lepton and the muon. Why these values are as they are, we do not know, and the coupling constants, the strengths of the strong, weak, and electromagnetic interactions. They determine how particles interact and the probabilities of attraction, repulsion, or transformation. Changing even slightly would collapse the entire universe. If the strong interaction were slightly weaker, protons could not exist. If electromagnetism were slightly stronger, the chemistry we know would disintegrate. Additionally, there is the Higgs field's vacuum expectation value, how much it tends to exist. It is this value that determines the source of all particle masses. But the question is, why does the Higgs field's tilt exactly give the electron a suitable mass, yet not so large as to prevent light from propagating? Mixing angles describe how particles change identities under weak interactions. They dictate how neutrinos change types while traversing space, as if a person could switch passports at will. When moving from one country to another, this mechanism is simple to use, but feels eerie behind the scenes. All these parameters make the standard model's predictions astonishingly precise. When you plug them into equations, the calculated results match experimental measurements, accurate to 10 decimal places. It's like a piano staying perfectly in tune while a storm rages outside. But where does this tuning come from? One answer is no reason. These values are just as they are. The universe is just like this. The electron's mass is 0.511 MeV. You have to accept it. But most physicists are not satisfied with this. We want to know why. We want a theory that can predict these values, deriving them directly from first principles. This is what grand unified theories and string theory attempt. They aim to go beyond the standard model through deeper mathematical structures, reducing the number of free parameters, linking these seemingly independent values. But so far, no grand unified theory has truly succeeded. String theory even proposes a more unsettling possibility, that of a landscape of countless possible universes, each with different parameter values. In some universes, electrons are too heavy for atoms to form. In others, stars never ignite. Our universe is just one among them, and we can live here only because its physical conditions happen to be suitable for life. This is the so-called anthropic principle, not asking why these knobs are set this way, but asking why their settings allow life to exist. In other words, this is not an answer from deep physics, but a cosmic selection bias. But this explanation feels unsatisfying because it sounds like giving up on a real answer. If the universe must be finely tuned to a suitable state, then there must be a higher level theory behind it that can explain everything. Our exploration continues to the concept of running constants. Some physical constants are not fixed, but change with energy. For example, the strength of electromagnetism becomes stronger as particles get closer. If we could raise energy high enough, all fundamental forces might converge into a single force at some point. This is the core idea of grand unified theories. However, experiments so far have no evidence supporting it. The fine-tuning problem is also a mystery. If you slightly tweak some parameters, like the mass difference between neutrons and protons, complex chemical reactions become impossible. Stars cannot form. We would not exist. Is this just coincidence or some clue? And neutrinos? Their masses are extremely small, millions of times lighter than electrons. Some models think their mass origin is completely different from other particles. If true, then the standard model is not the full picture of physics. Some crucial parts are missing. In string theory, some even propose mother fields. These are variables hidden in the early universe that determine the values of these parameters. If these fields stabilized at some value after the Big Bang, perhaps locking in today's physical constants, But for now, this is all theoretical framework without experimental verification. Next, we encounter an even more mysterious number, that is the fine structure constant, a physical rule that seems without reason yet governs natural laws in science. There is a number that appears almost everywhere. It appears in quantum physics, atomic structure, electromagnetism, even equations describing how light and matter interact. It is not an integer, nor derived through simple methods, but it determines the strength of electromagnetism, and electromagnetism is probably the most important force in everything we see, feel, and rely on. This number is approximately 1/137th, more precisely 137.035999206. Physicists usually call it alpha, directly alpha, also known as the fine structure constant. This is one of the strangest, most mysterious constants in the universe. We know how to measure it, know how it affects physical processes, but completely do not know why it has this value. Alpha is a dimensionless constant. It has no units, not meters, not seconds, not kilograms, but a pure number like pi or e. This is key because it means alpha is universal. Even if we meet aliens tomorrow, their physics would also use the same alpha, even if their unit systems are completely different from ours. So what does it actually do? Alpha determines the strength of interaction between charges. In other words, it tells charged particles like protons and electrons how to attract or repel each other. It also affects how electrons move in atoms, including their transitions between energy levels, how they emit and absorb light, and how far they are from the nucleus. Without alpha, chemistry cannot function, matter and light cannot communicate. All structures made of atoms would fall apart. In atomic physics, alpha determines the fine splitting of hydrogen spectral lines, which is where its name comes from. In quantum electrodynamics, it appears in calculations of electron-photon exchange and vacuum interactions. In fact, one of the most precise predictions in physics, like the electron's anomalous magnetic moment, depends on accurate measurement of alpha. Yet where does it come from? We completely do not know. Unlike pi, which can be derived from circle geometry, or the gravitational constant, which has a clear mass-force relationship, alpha is not derived from some deeper equation, not determined by symmetry, nor a simple ratio of other constants. It is directly measured. We point instruments at reality and say, it looks like 1/137th. This number has troubled scientists for over a century. The famous physicist Arthur Eddington was obsessed with alpha, firmly believing it must originate from some deep logical rule, fundamental to how the universe works. He even tried to derive its meaning through pure mathematics, thinking 137 was the key to some cosmic code. His theory did not come true, but interest in alpha never faded. Richard Feynman once said, "Since its discovery, it has been a mystery." All good theoretical physicists put this number on their wall, and worrying about it every day. To this day, the fine structure constant remains one of the most precisely measured numbers in science. Accurate to 1 part in 100,000, yet its origin remains completely unknown. Some physicists hope a future theory of everything, will naturally derive alpha from first principles, perhaps in string theory, quantum gravity, or some deeper unified theory. But decades of effort have passed. No theory has been able to calculate it accurately, at least not yet. Others speculate alpha might change over time or space. If true, perhaps it could help trace its origin. Scientists have observed light from quasars billions of light years away to see if alpha was slightly different in the past. Some data hints at slight variation. Other data shows no change at all. We still have no conclusion. Another view is the anthropic explanation. If alpha were slightly larger, atoms would be unstable. If it were smaller, stellar nuclear fusion might not proceed normally. The physical conditions required for life are very stringent, and the reason we can observe alpha is precisely because we happen to live in a universe that allows it to take this value. But this is not an explanation, just a description of survivor bias. The mystery of alpha is part of a larger puzzle. Nature's fundamental constants seem arbitrary, yet determine the behavior of everything. The speed of light, gravitational constant, Planck's constant, the masses of electrons and quarks. These are all hard to explain, but what's special about alpha is it links quantum theory, electromagnetism, and relativity together, yet still refuses to tell us where it comes from. Is gravity geometry's built-in property? This was Einstein's great leap. In the early 20th century, people generally thought gravity, like other forces, was a mysterious force acting at a distance. Back in the 17th century, Isaac Newton described gravity mathematically, but he himself admitted he didn't truly understand its essence. Gravity could make Earth orbit the sun and make apples fall from trees, but what is its root? No one knew. In 1915, Einstein published General Relativity, completely redefining gravity. It is no longer a force, but a result of spacetime's shape. From this perspective, massive celestial bodies are not pulling each other, but bending the fabric of reality. Other objects just naturally move along this curved path. This was a radical shift in thought. Gravity is no longer a long-range force, but becomes a property of geometry. Imagine spacetime as a rubber sheet. Place a bowling ball in the center, the sheet sags. Now roll a marble nearby. It will approach the bowling ball along the sagging curve, not because of an invisible pull, but because its path is curved. This is the classic analogy for Einstein's view of gravity. But this is not just a visual metaphor. It also produced verifiable predictions. Light bends near massive celestial bodies. Clocks tick slower in strong gravitational fields. Space stretches around stars and black holes for a century. These predictions have been confirmed again and again. Until 2015, LIGO directly detected gravitational waves from merging black holes, once again perfectly confirming Einstein's theory. So, does this mean gravity's explanation is complete? At least in the macroscopic world, general relativity performs very well. It explains GPS time corrections, planetary orbits, even the universe's expansion. But once we enter the quantum scale, things become messy. In general relativity, space-time is smooth and continuous and shaped by mass and energy. This is a classical theory's view. while quantum physics sees the world as discrete and certain, full of randomness. The two cannot be seamlessly combined. When you try to explain gravity with quantum rules, you get infinite energies, failing equations, and various physical absurdities. This is one of physics' biggest unsolved puzzles: how to explain gravity in the language of the quantum world. Some physicists think Einstein's vision is largely correct, but incomplete. Gravity might come from a deeper quantum structure, where space-time is not smooth, but composed of extremely tiny, discrete units, like pixels in a video game, or atoms in a lattice. In these models, the curvature we see is just the macroscopic result of countless micro-interactions. This sheet is not made of rubber, but digital. Others propose gravity might not be a product of geometry at all, but of information. From this view, space-time consists of quantum entanglement networks. These networks define far and near. Geometry is just a byproduct of how information is shared between different regions. Gravity is a manifestation of quantum information flow. This is not baseless. Theories like ADS, CFT duality suggest gravity can be seen as an effect related to thermodynamics and entropy, rather than pure geometric deformation. Does this mean Einstein was wrong? Not entirely. Just as Newtonian mechanics is still correct on Earth's scale, Einstein's theory remains perfectly applicable in the macroscopic realm, but may have its boundaries of applicability. The next theory might explain how gravity works at the deepest layers of reality's structure. If gravity really is space's built-in property, then we must also ask why such space, why for dimensions, that is, 3 spatial dimensions plus 1 time dimension. Why does curvature behave this way? Why is gravity's strength far weaker than other fundamental forces? If it originates from some deeper mechanism, what is its source? These questions are not just theoretical curiosity. They affect our understanding of black holes, the Big Bang, wormholes, and the universe's ultimate fate. If gravity really is geometry, then the universe is a dynamic shape evolving with time. If it comes from something else entirely, then space-time might just be an illusion of deeper laws, a shadow cast by foundational rules we haven't yet discovered. The laws of thermodynamics at first glance seem like simple, understandable rules. Heat flows from high temperature to low temperature. The total amount of energy remains constant. You cannot build a perpetual motion machine. But beneath these straightforward rules, physics hides a deeper question. Are these laws really the universe's fundamental principles, or just the result of more complex statistical behavior? Let's start with the most familiar second law. Entropy always increases. Simply put, this means systems spontaneously move from order to disorder. Ice melts, batteries drain, buildings collapse. The entire universe inevitably moves toward chaos. Yet at the microscopic level, the physical laws governing particles, atomic nuclei, fields, are time-symmetric. That is, they do not care whether time moves forward or backward. If you film a process of particle interactions, then play it backwards, the physical laws still hold. The mathematics still works. Then why does entropy always increase in one direction? This is one of the strangest facts in physics. On the whole, The world seems to have an irreversible arrow of time, yet at the smallest scales, everything can be reversed. Some scientists believe the second law is not a hard cosmic rule, but a statistical trend when you have enough particles. What is the most likely thing to happen? Like a deck of cards, only one arrangement is perfectly ordered, but there are trillions of disordered arrangements. Given enough time, disorder is almost inevitable. This is entropy. From this perspective, the second law is not some mysterious cosmic principle, but a natural manifestation of probability theory on chaotic systems. The universe is not forced toward disorder. It just almost always does. This concept of emergence appears elsewhere too. Like temperature, a single particle has no temperature. But when you have billions of particles constantly moving, their average kinetic energy becomes temperature or pressure. It's just the average effect of countless tiny collisions. Thus, perhaps those thermodynamic laws, energy conservation, entropy increase, heat flow, are not fundamental laws engraved on the cosmic foundation, but results that only appear at macroscopic scales. However, some physicists think the second law might be more fundamental than we realize, perhaps even more fundamental than time and space themselves. This is because entropy occupies a central position in black hole physics. In the 1970s, Stephen Hawking discovered black holes are not completely dark. They radiate energy. This radiation is now called Hawking radiation. More importantly, he and Jacob Bekenstein found black holes also have entropy, and its entropy is proportional to the black hole event horizon's area, not its volume. This hints that all information about what falls into a black hole seems to be stored on its surface, not inside. This directly leads to the famous holographic principle. The entire universe might be like a holographic projection. Physical information in the volume is encoded on a lower dimensional boundary, and at the core of this theory is precisely thermodynamics. In fact, some researchers now think gravity itself might be an emergent thermodynamic effect. In 2011, physicist Eric Verlinde proposed gravity is not a fundamental force at all, but an entropic force arising from information and entropy changes. In this model, objects move closer not because of some mysterious pull, but because such motion increases entropy. If true, then thermodynamics is not just simple kitchen physics rules. It might be the entire universe's operating system, the engine from which space-time and gravity are born. So which is it? If Newton's laws can tell an apple how to fall from a tree, can they also tell thermodynamics how to govern the entire world? And as for emergence, is it just a phenomenon that appears when systems are large enough, complex enough? These questions have no simple answers, but they force us to rethink what a physical law really means. Rules like the speed of light limit or charge conservation, must they exist from the universe's birth, or did they emerge only after the universe became sufficiently complex? This leads to another question: the physical laws of the early universe, were they the same as now? Imagine the first few seconds after the Big Bang, no stars, no galaxies, not even light or atoms existed. The entire universe was an extremely hot, boiling ocean of pure energy. Space and time had just begun to form. The physical laws we know today might not have existed at all then. This is not science fiction, but one of cosmology's most profound and serious questions. Did physical laws gradually emerge over time? If so, were they completely different in the early universe from today? To understand this, we must talk about unification. The four fundamental forces we know today: gravity, electromagnetism, strong nuclear force, weak nuclear force, probably were not always separate. In the extremely hot environment after the Big Bang, they might once have been a single force, indistinguishable from one another as the universe expanded and cooled. This unity gradually broke, like metal cracking as it cools. First, gravity separated earliest, possibly at the Planck time after the Big Bang, around 10:43 seconds. Then around 10-36 seconds, the strong interaction separated. Later, the electrowake force, a fusion of weak and electromagnetic interactions, split into two forces. This process is called spontaneous symmetry breaking, one of the most important ideas in particle physics. If today's various forces are products of broken symmetry, then the laws governing them must have been different in the early universe. The equations we use today to describe gravity or electromagnetism were not applicable in the early universe. They became what they are today only after these symmetry-breaking events. Not only forces, physical constants back then might not have been fixed either. Light speed, gravitational strength, particle masses might have still been changing. Some theories even suggest the constants we take for granted, like the fine structure constant or gravitational constant, might have gradually frozen as the universe cooled. A classic example of this idea is grand unified theory, and such theories, strong, weak, and electromagnetic interactions, are actually different manifestations of the same force, described by a single grand symmetry group. This symmetry only holds at extremely high energies, trillions of times higher than energies humans can produce in labs. When energy falls below this threshold, symmetry breaks. The three familiar forces we know today each emerge in the early universe. There might also have been processes similar to phase transitions, like water freezing when cooled. Space itself might have experienced freezing points, instantly changing its own structure. These phase transitions might leave special relics, like topological defects or exotic particles, and might even explain why matter exists. The inflationary period was an event related to an important phase transition, an extremely brief moment after the Big Bang. The universe entered a phase of exponential expansion. During this time, space expanded even faster than light. Inflation smoothed space, making the universe overall flat, and might have prompted fundamental forces to separate simultaneously. It might have locked in some states of the early universe, including certain key values in physical laws, or the Higgs field. Today, the Higgs field gives particles mass, but in the early universe, before symmetry breaking, the Higgs field's value was 0, meaning all particles were massless. The equations of motion back then were completely different from today. Only after the Higgs field stabilized at a non-zero value did particles gain mass. This also means Physical laws transform from one form to another. These phenomena, now hundreds of billions of years past. Why are they still important? Because they remind us those seemingly universal, unchanging physical constants might just be products of special conditions in the early universe, just as today's landscapes and climate were shaped by ancient ice ages. This also opens the door to a bolder idea. What if other regions of the universe, or even completely different universes, have drastically different physical laws? In the multiverse hypothesis, different space-time bubbles might have experienced different symmetry breakings. Some places have more forces. Some might have no forces at all. Some might not even have space or time as we know them. Thus, our physical laws are not the universe's underlying rules, but products of environment. Even if we can never directly reach those regions, we can still glimpse early universe secrets by studying cosmic microwave background radiation, the afterglow of the Big Bang. The tiny fluctuations in this radiation might preserve imprints of past phase transitions. By analyzing them, perhaps one day we can truly confirm whether the universe's physical laws have evolved over history. Perhaps the universe's rules are not truths carved in stone, but temporary answers floating in the river of time. When new laws emerge, old truths collapse. We will discover those rules we worship as unchanging are but a few lines of annotation in a larger script. So the real mystery is never why the universe follows rules, but who or what decides when the rules should change. When that moment comes, perhaps even the language we use to ask questions will be redefined. All right, my friend, let's pause our conversation here tonight on the mysteries of the universe. Now, allow me to press pause for you. Set aside all thoughts and inquiries and simply, quietly be in this moment. From here, my voice will fade away, leaving only the silent tapestry of the cosmos and a carefully chosen piece of pure music tuned to 432 Hz. Science suggests this frequency resonates deeply with the natural vibrations of the universe and the rhythm of life itself, soothing your nervous system and guiding you into deep relaxation. Now, find your most comfortable position. Gently close your eyes or let your gaze rest softly upon the stars. May you release all weariness from the world, letting your consciousness drift on the waves of music, floating into boundless tranquility. Good night, sweet dreams, until we meet again among the stars.